All right, so in this discussion, in this video, we are going to solve a number of problems based on entropy and the free energy. So the first problems will be predicting the sign of entropy change if you are given a chemical reaction. So normally, if you are given a chemical reaction, what you should look for is how many gas molecules are in your product and how many gas molecules are in your reactants. So the gas molecules will give you an idea what changes in entropy you are going to have. And another thing you need to look at is, do I have a solid and do I have an aqueous solution? So if we start with A says we have water gas to give us water liquid. So in this case, gas phase is reactant. Gas phase is reactant. This implies that the reactant has higher entropy than product. So it implies reactant has higher entropy than product, because water gas phase has higher entropy than water liquid phase. What does it tell us? It tells us that the change in entropy is going to be less than 0, because we are moving from higher entropy to low entropy. Now B, solid carbon dioxide sublimes. In this case, we are moving from solid to gas. Therefore, we are increasing entropy. So this tells us that the delta S, or the change in entropy, is greater than 0. What about in C? In C, if we count the gas molecules, in C we have 2 gas molecules on the reactant side. So 2 gas molecules on the reactant side, but 3 gas molecules on the product side. So this tells us that the product has higher entropy. So therefore, product has higher entropy. What does this say? This tells us that delta S is greater than 0. Every time the product has high entropy, the delta S is going to be greater than 0. If we go to D, for D, we have H2 gas and Air2 gas to give us 2 2Hi, also gas. In this case, we have two gas molecules on both sides. This tells us that the delta S is approximately equal to 0. So the change in entropy will be equal to 0 because on the left side we have two gas molecules, on the right side we have two gas molecules. In terms of E, we are moving from solid to aqueous. So in this case, we are increasing the entropy. So here we are increasing entropy when we move from solid to aqueous. So this tells us that delta S is greater than 0, or the entropy is going to increase. So here we say predict the sign of the entropy. Here the sign of the entropy will be negative, while the sign of the entropy here will be positive. Here it will be positive. Here it will just be 0. Here it will be positive. So whenever entropy is greater than 0, that is a positive sign. Whenever entropy is less than 0, that is a negative sign. Now let's move on to the next problem. In this problem, we are calculating entropy changes in the surrounding from a reaction equation. Here, we are given a combustion reaction equation here. Then we are given the enthalpy or the delta H of the reaction. We have to solve three problems. The first one, calculate the entropy change in the surroundings when this reaction occurs at 25 degrees Celsius. So we are given our temperature here as 25 degrees Celsius. The second problem, determine the sign of the entropy change for the system. The third problem, determine the sign of the entropy change for the universe. And the question is this reaction spontaneous? So that is our question. So we have a combustion reaction in this case. So let's look at the combustion reaction and make a determination based on these questions. So for the first question, for A, so for A, we know that the entropy of the surrounding is given by negative delta H of the system divided by T. This one should be given in joules. You don't want to use kilojoules in this equation. And the temperature here should be given in Kelvin, 298 Kelvin. So when you are given temperature in degrees Celsius, you need to change it to Kelvin. Now, if we plug in the numbers here, we are going to have minus 2044000 joule divided by 298 K, which gives us minus 6859 Kelvin. So this one will say that the delta S of the surrounding is equal to negative 6859 Kelvin. Actually, there was a simple issue with solving this problem that I need to address a little bit. So I will erase this part and also this part. So here we are saying delta H surrounding is given by negative delta H system divided by T. But this is the delta H system and this is the temperature. So here we have a negative, then we have inside here negative 2044000 J. So I forgot to put a negative inside here. Divided by 298 K. And because of that, this one is going to give us a positive 6859 joules per Kelvin. So we are going to obtain a positive entropy, not negative entropy like we did at the beginning. So joules per Kelvin. Here we can say that delta S surrounding is equal to plus 6859 K. So that is question A. Question B says determine the sign of the entropy change for the system. So to approach this question, you need to look at the reaction equation. If we look at the reaction equation, we see that we have 5 gas molecules. So we have 5 gas molecules as reactants and 7 gas molecules as products. That's what we have. This tells us that products have higher entropy. Products have high entropy. Therefore, the sign will be positive. So the sign will be positive. So this is the sign of the entropy change in the system. Because to determine the entropy change in the system, you look at the reaction equation itself. So this reaction has higher entropy has positive entropy of the surrounding, also has positive entropy of the system based on the reaction equation itself. Now, number C. It says determine the sign of the entropy change of the universe. We know that delta S univ is given by delta S system plus delta S surrounding. But both system and surrounding are positive, as we have seen. We see that this surrounding is positive here and the system is positive. Therefore, so I'll say, since both system and surrounding are positive, this implies universe is also positive. So the sign of the entropy change for the universe is positive. So the last question is this reaction spontaneous? So is the reaction spontaneous? The answer is yes. The answer is yes, because entropy of the universe increases in a spontaneous reaction. That's what the second law says. Entropy of the universe increases in a spontaneous reaction. Now, based on that, this reaction is spontaneous. So that's the second problem, entropy problem, that we need to be able to solve. What is the third problem? In the third problem, here you are given a reaction equation, and based on the reaction equation, you want to calculate the entropy, the overall entropy change of a reaction using like in this case, two-step reaction. So these are the two-step reactions to give us the overall reaction. So we have a two-step reaction here. Now this is the overall chemical reaction here. This is our overall chemical reaction. But to get to that overall chemical reaction, we passed through these two steps. So step one, so the overall chemical reaction is 2 carbon monoxide plus 2 nitrogen monoxide to give 2 carbon dioxide and nitrogen. But this went through two steps. It went through the first step here and the second step here. So it's like Hess law. So these two steps are going to add up to give us this reaction here. That's what we are saying. Now, the question is, calculate the entropy change of the overall reaction using the reactions 1 and 2. How do we do this calculation? The first thing we do is to inspect our reaction. So 1, we'll say this reaction here has carbon dioxide here. So it has 2 carbon dioxide. And we go down here to look at these reactions. This reaction also has 2 carbon dioxide. Both carbon dioxides are reactants. So what this tells us is this reaction 1, we leave it as it is. Leave it as it is. Because we have carbon dioxide here as a reactant, we have carbon dioxide here as a reactant. And we have 2 carbon dioxide here, we have 2 carbon dioxide here. So because of that, do not tamper with reaction 1. So I'll just write it here as it is. 2CO gas plus O2 gas to give us 2CO2 gas, and then the delta S is equal to negative 173.4 joule per Kelvin. Now let's look at the second equation. For the second equation, we are going to use nitrogen here. Do you see nitrogen here? This nitrogen here is present as nitrogen here also. We have 1 nitrogen here. The only difference is that the nitrogen here is a product, the nitrogen here is a reactant. So we need to make this nitrogen a product. So that, the nitrogen here is a product, here is a reactant. We need to make this nitrogen a product. But because we have 1 nitrogen here and we have 1 nitrogen here, we don't need to do any multiplication of this equation because we have the same number of nitrogens. Now, because nitrogen is a product here, we are going to reverse this whole equation so that nitrogen is on this side instead of being the side where it is. So the equation becomes 2NO gas is equal to N2 gas plus O2 gas. And since I have reversed this equation, I am also going to reverse the delta S. So the delta S here becomes negative 24.5 joules per Kelvin. So negative 24.5 joules per Kelvin. So in the end, what I want to do is I am going to add these 2 equations and see if it is going to give me the overall equation here. So how do I do that? I have carbon monoxide here and nothing is cancelling carbon monoxide. So I'll put my 2 carbon monoxide gas. I have oxygen here, but this oxygen on this side, the oxygen that is on the left side cancels with the oxygen that is on the right side. So things in the left side must cancel things on the right side. What else can cancel in this case? There's nothing else that will cancel. So on the left side here, I have 2 carbon monoxide and 2 nitrogen monoxide, which is also a gas. That gives me 2 carbon dioxide here and nitrogen. And nitrogen. So what I do with the entropies, I will just add them. So when I add the 2 entropies, the final entropy of this reaction becomes negative 197.9 joules per Kelvin. So that's how we solve a 2-step reaction to give us an overall chemical equation. We solve it like we do Hess law in thermochemistry. Let's look at another example. In this example, we have the overall chemical equation. Given here, this is our overall chemical equation. But we can obtain the entropy of this chemical equation by using the 2 reactions below, reaction 1 and reaction 2. So it's just the same process. This one will be a little more complicated than the first process. So the first thing you want to do is do the inspection again. So I'll look at the sulfur here. We have 1 sulfur here. And we look at these 2 reactions and see which one has sulfur. We see that we have sulfur here, S. The problem is we have 2 sulfur instead of having 1 sulfur. So what do? You multiply the whole thing by half so that you should have 1 sulfur. You don't want to have 2 sulfur atoms in these 2 reactions when the overall reaction has only a single sulfur. So when I multiply by half, I am going to have sulfur S plus 3/2 oxygen gas to give me SO3 gas, and then the delta S will be equal to the one that is given there divided by 2. So minus 166.2 divided by 2, which is minus 83.1 joule per Kelvin. Now I'm done with reaction 1. Let me go to reaction 2. For reaction 2, what do I look at? I'll look at this sulfur dioxide. This one has sulfur dioxide here. It also has sulfur dioxide here. But we have 1 sulfur dioxide here. We have 2 sulfur dioxide here. Now, the sulfur dioxide here is a reactant, while the sulfur dioxide here is a product. Because of that, what I am going to do is to reverse this reaction and then divide it by 2. So first, I divide this reaction by 2, and then I'll reverse it. So after reversing, I am going to have SO3 gas, because I have divided the whole reaction by 2 and reversed it. SO3 gas to give us SO2 gas and half oxygen, which is also gas. So the delta S of this reaction, this negative here will reverse to become positive, and then you divide this whole thing by 2. So 188 divided by 2, which will become positive 94 joules per Kelvin. Now I am going to add the 2 reactions. So in terms of adding the 2 reactions, the sulfur is not cancelling with anything, so it will just be sulfur here. So we have sulfur solid plus this oxygen cancels part of the oxygen here. So this one goes and there'll be 1 oxygen. So we'll have oxygen here. And then this one, the sulfur trioxide here, will cancel with this one here. So that one is gone. The only thing we are remaining with here is the SO2 gas. And the entropy change will be the addition of the two entropies there. So 94 minus 83.1, which gives a positive entropy of 10.9. So that is how we solve entropy problem, where you are required to calculate the entropy change when you are given the overall reaction. So in the next video, we'll see how to solve more problems based on entropy and also other problems based on free energy.